So we can start this demo session with Dr. Peter Baptist from the Mathematical Institute at Chair of Mathematics and Mathematics Education at the University of Bayreuth in Germany. They have a very interesting proposal to show us how to teach mathematics. I would say following the exposition of Hannes in this kind of transdisciplinary way. So because they use mathematics, arts, and it's a very, as we said this morning, a very inspiring way to teach. So I'm really happy to have him there because I was following a little bit, thanks to Emma, this project, and I have to say I love it. So the floor is yours.
Well, thank you very much for this kind invitation, and I want to tell you a little bit about one of our projects. Originally, I wanted to talk about what do we learn from SINUS, but on Sunday evening, I got a mail from Emma, and she told me, I want to hear something about your math and arts project. And I was on a journey, and I had some difficulties to make a new presentation, so you get a mixture between SINUS and math and arts because everything belongs together. I hope you will understand it after my short talk. Well, first I want to show you where I live and work. I live and work in Bayreuth. Bayreuth is in the northern part of Bavaria, about 250 kilometers north of Munich. And our university is comparatively young. It was founded in 1975, much older, 100 years older, and therefore I think more known in the world is the Bayreuth Opera Festival. And I think it's the only opera house in the world. It's only used 6 weeks a week and only for the operas of Richard Wagner. Well, but I'm not talking about music. I want to talk about math and why do we need new ways for teaching math. And I think many people have not an accurate picture of what mathematics is. Many people view mathematics as a set of methods to be applied to a list of problems at the end of a textbook chapter. And I think you know all these pages from the time when you went to school. And I think the reason for this misadjustment is the way how mathematics is often taught. And teaching from the blackboard, demonstrating a method, and then the students have to do about 20 similar problems. Well, we can ask how can mathematics teaching become more educational and less draining? And in Germany we had the SINUS project, and we had there 1,800 schools for 9 years. And it was really a tough problem. And I had to travel a lot in our country. And here you get a short glimpse of an article, not of a math journal. It is Die Zeit. It's a newspaper, a weekly newspaper in Germany. And they said realistic problems instead of mechanical computing, individual and independent learning instead of stubborn formula training. These are the characteristics of math teaching in SINUS. And this article was not written by me or one of my colleagues. It was written by journalists. Well, if you want some information on this project, we still have a web page, and the web page is actual still, and it's sinus-transfer.eu. Well, for us, teaching is an active, constructive, goal-oriented and cumulative process. The teacher is not an entertainer, the student is not only a consumer. I only have here half an hour, therefore I'm an entertainer now. For teaching you need more than half an hour, I'm so sorry. Well, instead, rather than showing the students only facts or a smooth path to a solution, the teacher should guide the students via well-elaborated problems through a journey into mathematical discovery. And in July, we started an online publication of SINUS documents, and every 3 months there are new documents published there. The address you can see here, and I have here a lot of brochures for you, so you can get some information and you can read everything what we have done here in the SINUS project. Well, school is more than a place for lecturing, school is a place for learning. How can we start such a learning process? And I like to cite my American colleague Paul Halmosh. He says, don't preach facts, stimulate acts. Stimulating acts means to ask students to explore, to observe, to discover, to conjecture, to explain, to prove. All these activities here can you have in natural sciences as well. In mathematics, we have the good opportunity to prove what we have done. That's an advantage of mathematics. Well, here you see some examples of stimulating acts. I only want to show you one example of dynamic worksheets. We have experiments on the computer screen. On the left-hand side, you have a dynamic applet. On the right-hand side, you have instructions, hints, something like that. And then a very important thing is the students have to do records in a study journal. I'm very old-fashioned, not in an electronic study journal. I think it's very important to make sketches, to write with your hands. It's better for the mind. The students use study journals for sketching meaningful figures, describing their observations, phrasing conjectures, writing down proofs, expressing individual impressions and comments. Well, I know in Spain golf is very popular, therefore I choose an example from golf. Here you have the surface of a golf ball. The surface is not smooth, it's uneven, it's covered with so-called dimples. These dimples are very important because the golfers want the balls flying high, long, and so on. And there's done much research work how the shape of these dimples is. And some years ago, there was an ad in a golf magazine, and the colorway company said, a revolutionary concept for golf ball surfaces, hexagons. Well, as a mathematician, I said, oops, hexagons. Well, for colorway, a hexagon is a regular hexagon. And if you look at the vertex of a hexagon, you can add 2 other hexagons, and then you get a close covering here. You can go on to all directions and get this structure. This is a tessellation of the plane. The golf ball is round. It's a kind of magic by the colorway company. But the ad had a second page. And here we see the grid of the golf ball surface. And we see the ad was not so correct because you can discover here between all the hexagons some pentagons. Yeah. Well, here one and some more. Well, this is a fake because on the surface of the golf ball is covered with spherical triangles, and in the edges of the triangles are pentagons, and in between there are hexagons. You know a similar structure of the old-fashioned soccer balls. Well, let's go back to the tessellation with the hexagons. I think it's a very interesting shape. We go to the center of a hexagon and connect the center with every second vertex. And you see, we get a three-dimensional impression. And the impression gets stronger if we use colors. And now we enter the art gallery. And this is the first painting of Eugen Joost, a Swiss artist. I worked together with him. And we use this picture for school as well. And here you can see how we work in schools. We have their roll-ups, like the roll-ups you see here. The upper part, there's a digital print of a painting of Eugen Joost. And on the lower part, we have hints, we have remarks to the topic of the picture, remarks to mathematics. And this month, there starts a journey of these roll-ups through all German schools in Spain. And even we have two schools from Switzerland in Spain, one in Barcelona and one in Madrid, and they get this exhibition as well. So it will come to Barcelona. Well, we had here a tessellation of the plane with straight boundaries. The next picture in our art gallery shows boundaries which are not straight, that are curved. And now let's have a look in the studio of the artist, how this tessellation is produced. And the basic element of this picture is a square. We start with a square and then the incircle of the square. We halfen the incircle and we move the half circles. Well, we duplicate the pattern, we rotate, we give new shades, and we add further basic patterns. And now you have seen how the artist may have constructed his painting. Well, now we move the grid and we get a new shape. And now we do some mathematics. I want to know the area of this new shape. But I don't want to compute, because mathematicians can't compute, you know. Well, you have to look at the picture, you have to do some geometry. Now you see, this shape is half the square, it's a rectangle. And by the Pythagorean theorem, I know you know this theorem from your time at school, and with the Pythagorean theorem, you can square a rectangle, and therefore, you can square this figure. And this is a very ancient and very famous problem, not squaring this figure, squaring a circle. And this picture, squaring a circle, we also meet in our art gallery by Eugen Joost. Squaring a circle has something to do with the number pi, and of course there's a picture with the number pi, and this is an example of an irrational number that every student has to know, because often people say natural numbers is okay, fractions are okay. Why do we need irrational numbers? We need irrational numbers to compute the area or the circumference of a circle. Well, and here you have many numbers, and therefore I want to play a little bit with you with numbers, because it's here an active presentation. And we have a look at another painting in our art gallery. Well, this is an example of a magic square, and I want to explain to you what a magic square is. This is a 10 times 10 magic square, and we start with the easier one here in the middle. we have a 3 times 3 magic square. What is it? Well, we have a square divided in 9 smaller squares, and we put down the numbers from 1 to 9. Well, this is a little bit boring, therefore we play a little bit. Well, what has happened now? Look at the first line. Now it's your turn. You have to add, very complicated, I know. 2 plus 7 plus 6 makes, great. 9 plus 5 plus 1 makes, Emma, it's your turn. Okay, you see it's a little bit boring. The sum of the rows, the sum of the columns, and the sum of the diagonals is always the same. It's a magic number, it's 15. This makes a magic square. For a mathematician now, it's interesting how many different magic squares, 3 times 3, exist. It's only one, because when you rotate or reflect, it's the same. But if you add one line and one column, and you have a 4 times 4 magic square, you have about 880 different magic squares. And a 5 times 5 magic square, there you have, I think, some million examples. It explodes from 3 to 5. It's really astonishing. Well, but for an artist, it's very boring, a magic square only with numbers. And therefore, he chooses symbols instead of some numbers. And here we have a 3 times 3 magic square by Eugen Just. Well, let's go back to the 10 times 10 magic square. You see, here are some numbers. We have 10 times 10 small squares. That means we have the numbers from 1 to 100. But you see, we have many patterns here. And now it's really an interesting task to find out which numbers are hidden behind the single patterns. And it works, really. But I think I have not the time now to figure out with you all the numbers behind, but you have to have something as homework. Well, don't preach facts, stimulate acts. Here we have another picture by Eugen Just. Discover patterns and interesting numbers, investigate their properties. Here's so much hidden on mathematics in this picture. I only want to show you some examples. Here, for example, we have the number 10 with fingers, with dots, with slashes, Roman numbers, because 10 is a base for our number system. Then Eugen Just loves number biographies. Here you have several representations of the number 6. And you can find, I think, much more. Here you have hidden the Fibonacci numbers. If you don't know the Fibonacci numbers from your school time, you know the Fibonacci numbers from the book, The Da Vinci Code, or you have seen the movie with Tom Hanks. Here we have the scene in the book. Here are the Fibonacci numbers, not well ordered. And these two lines, the letters are not well ordered also. If you rearrange these letters, you will have Leonardo da Vinci. And if you rearrange these letters, you have the Mona Lisa. And if you rearrange the numbers in the first lines, you have the Fibonacci numbers. Well, Dan Brown is a clever guy. In our art gallery, we have some other pictures as well for the Fibonacci numbers. On the right-hand side, you have the Fibonacci sequence. And the sequence is very easy. You get a new element if you add the two predecessors. 1 plus 1 makes 2. 1 plus 2 makes 3. 2 plus 3 makes 5, and so on. And on the left-hand side, the colorful squares are a geometric representation of this number sequence because the side length of these small squares is 1, 1, 1, 2, 3, 5, 8, and so on. And here you have the word girasole. Girasole is an Italian word for sunflower. And here you have the seeds of a sunflower. And you can see the seeds are ordered here in spirals, left-oriented and right-oriented. Well, I have to come to an end. Another example here, 3, 4, 5, 9, 16, 25. That's the reverse of the Pythagorean theorem, because 9 plus 16 is 25. You know, in a right triangle, the sum of the squares over two sides is a square over the hypotenuse. Well, difficult English word. Very interesting. There are so many symbols and numbers and only one word, 40. Why is there the English word 40 on this picture? If you don't know, it's hard to find out. In my knowledge, 40 is the only English word where the letters appear in alphabetical order. F-O-R-T-Y. Pardon? People say so. You have to do something for tonight, Emma. In German, it's very easy. Yeah? The first number, 1, is such a number. The next one is 8, 8. And perhaps, I do not know enough Spanish, perhaps you find such a thing in Spanish as well. And here we have self-descriptive numbers. What are self-descriptive numbers? This number here consists of 1 0, 3 1s, 2 2s, 3 3s, 1 4. It's a little bit playing with numbers, but I think for school it's very important to play with numbers that kids get a feeling for numbers. And so numbers are not so abstract for them. And therefore I think it's important to have such pictures to discover all these properties. Here, 628, 496, 8,128 is very interesting as well. Well, look at number 6. If you look for the divisors of 6, the divisors of 6 are 1, 2, 3, 6. Now you add the divisors, but not the number itself. There remain 1, 2, 3. 1, 2, 3 makes 6. The next number with this property is 28. The next is 496, and so on. These are the so-called perfect numbers. And now you can see what mathematicians may think. The first perfect number has 1 digit, the second 2 digits, the third 3, the fourth 4. Now they think the fifth perfect number must have 5 digits. And the first ends with 6, the second with 8, the third with 6, the fourth with 8, the fifth has to end with 6. But this is the fifth perfect number. And up to now, we don't know how many perfect numbers exist. Well, that's an excursion to a completely other topic. The picture is called Hardy's taxi. Why Hardy's taxi? You know taxi. What is Hardy? Hardy is a very prominent English mathematician, and he met Srinivasa Ramanujan. That was an Indian genius. Ramanujan had no mathematical education, but he had a mathematical feeling. Till today, we are not ready with finding out all the findings in his manuscripts. And I only want to tell you a short story. I started 2 minutes later or 3 minutes later. I have still the time, I hope. Well, Ramanujan came to Hardy to England, and it was a very fruitful scientific discussion, but personally it was very hard for Ramanujan. He didn't like the English weather and he didn't like the English food because he was a vegetarian. But he could not go back to India. It was the time of the World War I, and at that time there were no planes, and because of the war he had no possibility to go by ship to India. And therefore he got ill and he was in hospital. And Hardy visited him, and he didn't know what to talk to Ramanujan, and therefore he said, the taxi I came to you had a very boring number. It was a number 1729. And Ramanujan said, oh no, Hardy, that's a very interesting number. That's the smallest number that can be written as the sum of 2 cubes. Well, 9 power 3 plus 10 power 3 equals 12 power 3 plus 1 power 3 equals 1729. It's easy to calculate, but to prove that this is the smallest number with this property took Hardy some days. And that's the genius of Ramanujan. We are not Hardy, we are not Ramanujan. I will show you something easier. If you count, or if you add the digits of 1729, 1 plus 7 plus 2 plus 9 makes 19. 19 is a divisor of 1729. And now find out other numbers that are divided by the sum of their digits. And there's still something special. 19 times 91, 91 is a mirror number of 19, equals 1729. Is there another number where the divisor is the sum of the digits and the complement is a mirror number? We started with a game and we are now deep in number theory. And I think that's fantastic in mathematics. And that's kind of mathematics you have to teach in school. Well, let me end. Math and arts approach is an educational model that enables students from kindergarten to university to explore properties of numbers, to discover and investigate patterns, to make guesses and conjectures, to discuss ideas with others, and to get a sense what math really is. And not to forget, math and arts offers many opportunities to enjoy math and to experience math in a productive way. Thank you very much.